In this video, we are going to look at the problem of force-directed scheduling. Now, force-directed scheduling is one of the heuristics which has been widely applied in the past several years to solve the overall problem of scheduling. Now, as we have already seen, the scheduling problem by itself is computationally intractable, meaning that if we have n tasks and some r different kinds of processors on which those tasks can be executed, in general, the amount of computation required to solve which task should go on to which type of resource can be exponential in the number of tasks and the number of resources that are available. So, people have proposed a number of different heuristics to solve this in the past. Force-directed scheduling was first proposed in 1987 by Paulin and Knight in the Design Automation Conference, and has since then proved to be a very robust and useful heuristic approach that can be used to solve the scheduling problem. You will notice that I am not calling it an algorithm. It is an algorithm technically in the sense that it is a well-defined sequence of steps. The problem why it is not usually referred to as an algorithm for scheduling is that it does not guarantee optimality of the solution. Alright, so before we get into the description of force-directed scheduling itself, we will just quickly recap a little bit about the scheduling problem and move forward from there. So what we have is, we are trying to solve the problem of scheduling. What we have is, as inputs, there are a set of tasks which I will call A subscript I, with I going from 1 to some number capital N. This is a set of tasks that need to be scheduled. In addition, we are given a certain set of resources R sub j, subscript j, where j is in the range 1 up to capital R, and this is resource types, meaning that a given resource type can perform a certain subset of the tasks that are available to us. For example, you could think of the different tasks as being additions, multiplications, divisions, possibly even something more complicated like a filtering operation and so on. And the resource types could be for an adder, a multiplier which can do only multiplications, an ALU unit which can do either additions or multiplications, and so on. Okay. And what you have in addition to both of these is dependencies, which are of the form AI to AK, which would normally be represented using some kind of a graphical notation where you would have nodes. This edge over here essentially indicates a dependency. What is the meaning of the dependency? It basically means that task AK can only start after task AI has completed. So, AK can start only after AI has completed. Alright, now in addition to all of this, we also have one last piece of information. How do the tasks and the resource types relate to each other, right? And what we can say over there is a certain tau I of, or rather a tau j of AI. This is the time taken to execute task AI on resource type Rj. And what does the scheduling problem itself require? What we need to do is to find a set of values. These values could be integers or real valued numbers depending on the actual values of the tau i's. What we are interested in is x of AI, right, such that x of AK is greater than or equal to x of AI plus tau j of AI. This is a mathematical formulation of what I just described in the previous section over here. Tau j of AI is the time required to execute task AI on some resource type Rj. there is an edge from AI to AK indicating a dependency. AK must start only after AI has completed, and we can capture this by this inequality, which basically states that the starting time x of AK must be greater than or equal to the starting time x of AI plus the execution time tau j of AI. Okay. So this is essentially the resource, the scheduling problem, and what we are overall trying to solve is a more complicated problem which includes the other two sub problems called allocation and binding. And allocation essentially says how many of each resource type are required, and binding says which instance of a resource should an operation or a task be mapped to. Okay. So the overall, even though I am just calling it scheduling, we have to solve all three problems: scheduling, allocation and binding, and usually they are all solved in one sort of combined manner such that all three, the final result solves all three of these problems. Now we have already looked at two specific or multiple different ways of doing this. There are two specific ways by which we can do this scheduling, the allocation and scheduling, which I want to recap quickly. Those are essentially the ASAP and ALAP, right? So the ASAP schedule is essentially as soon as possible, and similarly ALAP stands for as late as possible. These two schedules give us a lot of useful information which we can then use in order to build up other scheduling algorithms, and in fact in force directed scheduling we explicitly make use of this information. Okay, so let's get to the problem. The best way to discuss force directed scheduling is by taking up an example, right? And the example I am going to take is once again the differential equation solver. I am not going to go into the details of how the task graph is constructed. I am just going to straight away draw the task graph and use it. So what we have is there are a total of 6 multiplication operations. I am going to label them as M1 to M6, and similarly there are some other ALU type operations, either addition, subtractions or a comparison, right, which I will basically label as A1 to A5 because there are 5 of them. So we have M4, then we have M5. M5 output is used by A2. So all of these are directed edges. Similarly, what I can say finally is there is an M6 whose output is used by A3, and finally there are 2 more operations, A4 and A5. Note that in the original task graph these were different. I mean, some of them were addition, some were subtractions, one was a comparison, right? I am ignoring all of that and just sort of using either M or A. The reason is I am going to assume further that there are 2 types of hardware resources over here, right? So the hardware resource types available are the M type for multiplication operations, which has a latency or essentially finishes whatever multiplication it is required to do within 1 clock cycle. And similarly you have A type, which is ALU type operations, which also finishes within 1 clock cycle. Now with all of this information in place, we can straight away derive some useful information. For example, we can see that there is a critical path or a long path through this, the longest path through this particular task graph turns out to have a length of 4 time units, right? 4 clock cycles I am going to say in general, because I am assuming that each operation takes 1 clock cycle. But keep in mind that even if they, if you are not talking about clock cycles, you could think in terms of some abstract units of time, and all our analysis would still hold in that context. Anyway, the critical path for this particular graph is 4 clock cycles. With that in place, the ASAP schedule would look something like this. It would essentially say, I would take 4 clocks 0, 1, 2 and 3, and the operations that need to be scheduled in each clock cycle, I can basically say all the things in the first row of this graph, that is M1, M2, M4, M6 and A4, can be executed in clock cycle number 0. M1, M2, M4, M6 and A4, right? And then M3, M5, A3 and A5 can get executed in cycle number 1, A1 in cycle 2 and A2 in cycle 3. This completes all the operations that we need, right? In terms of resource requirements, the number of M type that we need over here is 4, and up here, and the number of A type that we need in cycle number 0 is 1. In cycle number 2 we need 2 of this and 2 of A type, 0 and 1, 0 and 1, which means that if I take the maximum values, I effectively end up with 4 multipliers and 2 adders as my requirement. The ALAP schedule, on the other hand, gives us some other useful information. It tries to execute each of the operations as late as it possibly can without violating any timing constraints. So the one thing we can straight away do is, for example, if I still want to meet a timing budget of 4 clock cycles, A2 can execute in the last cycle number 3, but so can A3 and A5. Now, after that, what it means is everything which is one step above that can execute in the previous clock cycle. So A1, M5, M6 and A4. A1, M5, M6 and A4 can execute in cycle number 2. If I go one step further, what I find is M3 and M4 can be in cycle number 1, and M1 and M2 we don't have a choice. They are on the critical path, they have to execute in cycle number 0. If I go back and do exactly the same diagram or the listing that I have over here, I have 2 multiplies, 0 adds, again 2 multiplies, 0 adds, once again 2 multiplies and this time 2 adds, 0 multiplies and 3 adds. So I end up with a requirement of a maximum of 2 and a maximum of 3 add type operations, okay? The question is, are either one of these optimal in any sense? And we know that the answer is no, right? We did not make any attempt to try and minimize the total number of resources. And in fact, if you look at these, you can probably think of fairly simple ways by which I could have reduced the resources in each of these different implementations. The one useful piece of information that does come through because of this is something called the mobility of the operation or the slack of the operation, right? In other words, I can define slack is equal to ALAP time of operation AI minus the ASAP time of operation AI, right? Which means basically that it will be equal to 0 for operations on the critical path and could be some integer for other operations, okay? Integer because it's number of clock cycles. And I'll also define the mobility as number of different cycles in which AI could have been scheduled. Right? In this case, basically that comes out to be the ALAP of AI minus ASAP of AI plus 1, in other words slack plus 1, right? So any operation that is on the critical path has a mobility of 1, it cannot move anywhere else beyond that, and the other operations would correspondingly have higher mobilities. This is not a strict definition of mobility, it is more something functional that we will just use for the purpose of defining something in the next step, okay? Alright, so now with this mobility, what I can do is I can go back, look at the task graph and say, okay, what happened? Why did the ASAP, for example, give me 4 multiplications as my requirement? Because it tried to put all the multiplications that were ready as early as possible, which was in clock cycle number 0, 4 of them. ALAP on the other hand ended up with a requirement of 3 A-type operations, A-type hardware units, because it tried to push all the A2, A3 and A5 into the last time step, right? Once again, maybe they could have been distributed differently. Okay, so with that in mind, we can now go back and basically look at is there anything in this mobility information that could have been helpful to us for rearranging these operations into some slightly better structure? Okay. So let's quickly try write down the mobility values for the different operations, right, because that will help us with our computations later. So for example, M1 from this graph has a mobility of 0, right, or rather a mobility of 1. Similarly, M2, and in fact everything on the critical path out here, right. So M1, M2, M3, A1 and A2. all have mobility values equal to 1. They can only be scheduled in one clock cycle. M5 could either be scheduled in clock cycle number 1, as you see in the ASAP schedule, or in clock cycle number 2 in the ALAP schedule. So it has a mobility of 2, that is M5. Okay. And similarly for M4 as well, M4 and M5 both have that same property. And after that, I'll just move over, yeah, I can just pull down here. Okay. What about M6 and A3? M6 for example could be here or anywhere up to here. So in other words, it could be at time 0 or at time 2. Okay. That basically gives it a mobility of 3 time steps, and the same for A3, and similarly for A4 and A5 as well. They both also have a mobility of 3 time steps. Okay. So how do we make use of this information? The problem that we are going to try and solve using this definition, using this new approach that we are calling force directed scheduling, is to say that subject to a latency constraint, that is to say I still have to fit everything within 4 clock cycles, right. So a latency constraint, I want to minimize the number of resources that I use. So it's a latency constraint resource minimization problem that I'm going to be looking at. Okay. How do we go about doing this? By using the concept of force. Now, what is force? Effectively, what I'm going to do in order to first define the concept of force is to say that I will now define something else called a distribution graph. Right? For M-type operations and for A-type operations separately. Each of these graphs essentially goes over 4 time units, 0, 1, 2 and 3. Right? And what it has is, I will look at each of the operations and put them on this graph spread out over all the clock cycles in which they could have been executed. What do I mean by that? M1 can be executed only in cycle number 0. So I'll draw M1 over here. It contributes a full 1 into cycle number 0. So does M2. What about M3? It has to be in cycle number 1 and will contribute its full effect into cycle number 1. A1 and A2 in their case will contribute to cycle number 2 and 3 respectively. So M3 in other words contributes here, and A2 and A3, which I will draw in the A operations distribution graph, contribute a full 1 into their respective clock cycles. Now, what about M4 and M5? Right? We saw that they have a mobility of 2, and what I am going to do is to say that M4 for example could have been either in cycle number 0 or cycle number 1, and M5 could also have been in either cycle 1 or cycle 2, right. M6 on the other hand could have been in 0, 1 or 2, which I will draw this way. Right, you will notice that it's getting sort of narrower as I increase the number of steps over which it is. That the reason is because I am sort of trying to keep the area in the rectangle the same. M6 is over there, which means that A3 correspondingly could also go into any one of these 3 clock cycles. And finally, I have A4 and A5. Okay. Now, with this information, I can essentially add up the total contribution that I have in each clock cycle and say this is 1 plus 1 plus 0.5 plus 0.333, giving me 2.833. Okay. What have I done? I have basically added up the total contribution corresponding to each of the operations. Intuitively, what this is saying is M1 has to contribute a full multiplication in cycle number 0, it cannot be moved from there. Similarly, M2, whereas M4 had a choice, it could either be in cycle 0 or cycle 1. So, I will sort of spread it out evenly to start with. Similarly, next stage I get 2.33 and here I get 0.83. Add everything together and I get 6, which is the total number of multiplications. What about the A-type operations? What I have is, I have 0.33 in the first, 0.3 plus 0.3 plus 0.3, so that is 1 in cycle number 2, again 1 plus 1, so 2 in cycle number 2, and in the last cycle I end up with 1 plus 0.33 plus 0.33, that is 1.66, right. And if I add all of these together, I end up with 5, which is the total number of A-type operations. Alright, now how do we use this information, right? By the way, the distribution graph for multiplication in cycle number 3 is 0. You cannot have any multiplications in cycle 3 and still finish within 4 clock cycles. Okay. Now, how do I make use of this information? This is where the force concept by Pauling and Knight came into the picture. Effectively, what they said is this number 2.83 or 2.33 can be thought of as something like a spring constant of a spring which is trying to push operations out of that particular time step. Okay. So, if there are more operations that or more contribution to a given time step, there is more likelihood that something needs to be pushed out for the system to execute well, which means that something with a 2.833 spring constant, any operation that you try to push into that time step will get pushed out even greater than if it was trying to be pushed into another time step that had only a 2.33 time constant. Okay. To understand this, let us take the example of operation M4, right. It had two choices, either time step 0 or 1. Okay. If we put it in 0, then what we are ending up doing is, now M4 contributes 1 to t equal to 0 and 0 to t equal to 1, right. So, effectively there is sort of a change in the distribution graph. Instead of that, the way that we think about it is, we say that there was a spring with the k equal to 2.833 and this is M4, which is basically trying to come in here and is getting pushed back by a force F is equal to k times x. Similarly, at t equal to 1, what is ending up happening is, here M4 is sort of trying to move out, it is being pulled back by F is equal to k times x, right. So, effectively what we have over here, in other words, is the net force that is going to act on this particular system is going to be 2.833 into how much is the difference that has been caused in terms of the contribution of M4 to step number 0. The new contribution is 1, the old contribution was 0.5, plus in step number 1, in time step number 1, the new contribution is 0, the old contribution was 0.5. Okay. And if we add both of these together, what we get is plus 0.25. Okay. The way to understand this is a positive net force is trying to push the operation out. It is not a good thing. Okay, it's saying that this was not a good move, but if it needs to be done, it needs to be done. Okay, but let us just consider what is the other choice that we have, right, which basically is if we choose step number 1. M4 now contributes 0 to t equal to 0 and 1 to t equal to 1, right, which means that the net force is going to be equal to 2.833 into 0 minus 0.5, right. This is a new contribution and this was the original contribution, plus 2.333 into 1 minus 0.5. When we add both of these up, what we get is that the result is going to be minus 0.25, and this minus is good. It's effectively telling us that there is something almost as though it's being pushed out of cycle number 0 and into cycle number 1, and the net force is such that it is sort of attracting it into cycle number 1. Okay. So, this already tells you how the concept of force is used. We can basically do this by trying out M4 in all the possible places in 0 or 1. I can do the same kind of computation for other operations. M1, M2, M3, A1 and A2 are fixed, they cannot be changed, but others M4, M5, A3, A4, A5 and M6, all of them I can try these out and find out which would give me the minimum possible force and use that in order to decide where to schedule that operation. Okay. There is one last step that we need to consider over here, which is when M4 goes into t equal to 1, the secondary impact of this is that M5 is forced into t equal to 2, right. In other words, M5 originally contributed 0.5 to t equal to 1, 0.5 to t equal to 2. Now, 0 to t equal to 1, because it cannot be in t equal to 1 because M4 is now in t equal to 1, and 1 to t equal to 2. Okay. So, I can define something called a successor force. What is that? It basically says that because I pushed M4 into t equal to 1, M5 in turn got pushed into t equal to 2. What is the net effect of that, right? This is going to be, what is the dg value in t equal to 1? It was 2.333 into new minus old plus 0.833 into new minus old. This corresponds to for M5, not M4. And if I do this computation, it basically adds up to minus 0.75, which incidentally is telling me that this was actually a very good move, because not only did I end up pushing M4 into step 1, getting a net negative force, that pushed M5 into step 2, which actually has a big negative force, meaning that M5 being pushed into step 4 is a very good thing. Intuitively, what does this mean? It means that step 2 has fewer multiplications in it than step 1. Pushing multiplications into step 2 is good if you can afford to do it. Okay. This pretty much captures the essence of the latency constrained resource minimization, right. Try all operations in each valid time step for that operation, compute the net force, place the operation with the lowest or most negative net force, recompute all the distribution graphs and go back to the first step until all operations have been scheduled. Okay. Similarly, you can also do something for the resource constrained latency minimization, but that's a bit more tricky because entire idea of distribution graphs can be computed only when you have a latency constraint. So what you do in resource constraint latency minimization is you choose some value for the latency and see whether the resulting force directed schedule would meet all your resource constraints. If it does, then you have actually solved the problem you started out with. If not, you increase the latency constraint by 1, recompute until you finally end up meeting the resource constraints that you have. Okay. So to summarize, force directed scheduling is one of the heuristics that has been applied very successfully to solve the scheduling problem. It's not the only one, but it turns out to have been very successful in practice.